Please confirm that my screen is visible or not. Okay, okay. Thanks. Thank you, guys. So I am Ashish Bajpai, PMRF from IIT Kanpur, and I am a live session tutor for this course, Computational Fluid Dynamics and Heat Transfer. So in this 12 weeks, there will be 12 live sessions. You can ask your question in every live session. And so one thing I want to confirm that I can't solve the questions which is asked in the uh, assignment of the week one right now in this session. So it will be a backlog session kind of. You can ask for some hints, that's possible, but yeah, I can't share the solutions for the like relevant purposes, as you know. So so any of you is having any questions, just let me know. uh, you can ask any question here, like till week one you can ask, or a journal CFD question if you have doubt in code. Yeah, please, like there is a lot of background noise. Chinmay. Yeah, now fine. Yeah, yeah, Chinmay, uh, you understood there is background noise? Yeah, Jai Shri. Chinmay, you have to, like, if there is some other system also connected, so it's a echo happening. So you have to reduce that, or you have to turn off one of your system. Then, yeah, you are audible. You are audible. Yeah. Mm-hmm. Sure. For radiation, I don't think so. There will be that kind of session in this. Maybe like if you want me to cover it, I can. Like I'm bit experienced in that, so I can cover it. But in the later sessions, after I think 4 5 weeks. Mm-hmm. Yeah, that's most important in that. Yeah. Sure. Like let me go through it. Uh, you can send me like whatever your requirements are, like because I know after some weeks there will be less people, so I can cover that after some weeks. um, but it will take time, that's for sure. So your radiative heat transfer. Okay, I'll share. Others, guys, all of you can ask question, any question from week one sessions or week zero assignment, which we solved. I think week zero was very easy, so it's fine. You can ask me from week one. I'll wait for some time. Then I'll just introduce you to some CFT uh, advantages, or you can say uses where we can use that CFT. Uh, so any of you can share your experience also for class, like how was the class, and are you getting it? Just a second. Okay. Yeah. Mhm. Mhm. Actually, it's a Chinmay. Actually, it's a rerun course. So currently, Gautam sir is not teaching it. I know because it. I think it was shoot in 2 years before, so he can't do it right now. But yeah, I'll share my point of view in CFD. So maybe you will get some more things. Yeah, so Venkateshan is joining. Others, guys, please be involved in this course because I can't just talking from my side. It's like keep on talking. Yeah, someone is Sn- Sanatha Kaki. Oh, okay, Sanatha. You can. You are raising. Yeah, yeah. You're audible. Yeah, you're. Yeah, yeah. Okay. Sure, sure. Okay, okay. Okay, okay. I understood. I understood. So what I will do, uh, I'll share my email ID. You guys can share your specific doubts, like specific things where you are finding. Like suppose, just I am giving an example, in that you can share that you are not able to understand. Suppose Navier-Stokes equations you are not able to understand. And most of you will know, but I'm just sharing this. So I'll share the whole. I'll teach the whole Navier-Stokes equation how to derive it, and then at the end what each term means. So I have some notes also that I will also share from last year's live sessions. I taught there lot of basics. It was just for 1 hour, so I managed it. But right now, this year it is more towards like conversation between us. So any doubt, you just share in the email ID. I'll share. Uh, in there, you can send me that you have this specific doubt. I'll cover that till that week only. Before that, after that, I'll not cover because like it should be after the lecture. So suppose some basic doubt is there that I will cover, like conservation equations. Yeah. Hmm. 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 It's a bit advanced course, so I will try to cover as much as basics as possible. And one more thing is like if in when I am teaching some basics, you can ask me question, stop me, ask me some question. Okay. Yeah, but for me, it's like if I am doing, because sir has already recorded, he can't again come and record it. So that's the thing. But for me, I will try to cover as much as possible. Yeah, yeah. Uh, yeah, I'll try to cover because I am feeling it will be a bit difficult for all of you to, like, not all of you are from same background, so I understand. Okay, okay. So you guys know about some like where CFD is used. I think all of you know. Or you guys can share some experiences where you are using or you are facing some problem like one guy told that he is facing in problem in radiative heat transfer. So uh, you guys can also share your experiences where it is used, or are you using somewhere? Any of you? Like, be free to ask question. It's I am just like you. Uh, uh-huh. Yeah. Yeah, yeah. Okay. Yeah, yeah, yeah. Okay. Yes, yes, yes. Sure, sure. Others? Mm-hmm. Yeah, there. Sorry to interrupt. There mostly people use finite element in the area you are using, and I am also in currently a part of that research. So what I am doing is I am using molecular approach, you can say, or mesoscopic approach. So there are three other types of approaches like CFT. CFT is a very large part, and that like right now what we are learning is a part of continuum which we read. But there are other approaches. So these are Eulerian approaches right now we are learning, but there are other approaches called as Lagrangian approaches. So in that, whatever you told me that re-entry problem, in that mostly people use molecular approach or Lagrangian approaches. In that, one approach is called as lattice-Boltzmann method, and another is direct simulation Monte Carlo method. So you can try using both. I'll like separately will tell you. Yeah, Arvind, you were also telling me some advantages of using CFD. Can you be a bit slow? I am not able to understand what you said. Sorry. Mm-hmm. Okay. 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 Got it. Got it. Very good. Yeah. Okay. This is a very nice application of CFD. It's a basic incompressible flow CFD. Yes. Yes. Nice. Nice. Other Harsh, Aero Engineer, Arun, anyone? Hema. Yeah. Yogendra. Yeah. Hi. Yeah. Okay. 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 So okay. So you are using a commercial software like Comsol? Okay. 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 Understood. Yeah. 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 Okay. Okay. Okay, okay. Yeah, yeah, it's needed there. Yeah. I'll share one application with you for solid rocket motor. So here you can see these are the applications. Uh, One of the applications of CFD. Okay, I'll share, take that. Uh, yeah, pointer. So you can see my pointer. So here you can see this is the solid rocket motor nozzle exhaust. So here some alumina particles are coming. So this is the, yes. So this is the direct numerical simulation of that solid rocket motor. That's one of the biggest problem right now. Motor rocket motor designers are facing. What you said? Yeah, it's my current research. So that I'm not sharing here. I'm just telling that this is not my research. This I have taken from internet. Oh, it's from Michigan State. I'll tell you. So I'll contact you, Chinmay, and you. I don't know your name, but Anand. Yeah, we can, like, you can contact me on email. Um, okay. Actually, your founder is from, like, I was also from IIT Kharagpur, so I met him. Skyroot, Pawan sir. Yeah, Pawan sir. Okay, so these are some of the applications. I'll start with this. So this is just a rocket flying, or inside the rocket, what is happening. Then when rocket goes into the space, that entry into the extraterrestrial environment is by rocket motors, you can say. Oh, sorry, by like, we will analyze that by CFT or different techniques of CFT. While landing, when plume comes out from the rocket, happening in Chandrayaan, it interacts with the surface, fluidize it. That also can be analyzed by CFD. This is combustion problem, which happens in, like, everywhere, in wherever we are using any of the jet fuels and uh, any burner. There we use the CFD for analysis of that. So the CFD can be used in three ways actually, uh, for turbulence analysis and all. So it is, one is RANS, Reynolds average Navier-Stokes solver. Another is LES, large eddy simulation, in which for turbulence we use larger eddies only. We can see larger eddies there. We will ignore the smaller eddies. And like this is a direct numerical simulation in which we are directly solving Navier-Stokes, but it is really expensive simulation. Another is like here, like whole helicopter is simulated with the help of CFT. So this is another kind of simulations. Now let's move further. So here in a wind tunnel, so during wind tunnel test, if we directly do experimentally wind tunnel test, it is very expensive, extremely expensive. But when we are doing the, suppose before that, for supporting the experiment, we are doing some CFD simulations. So we have defined a grid. So I'll tell this in, right now I'm telling it in a brief way. I'll tell it in a very uh, uh, like expand. I will expand that later. What is CFD? Why we are doing discretization? Just now you just see it, like we have a domain. We will discretize it, and then we will solve equation at each point there. That's a CFD right now. So here, what we have done in this, uh, it is uh, uh, it is a simulation of a jet plane, you can say, and here, or you can say fighter aircraft. Here we have divided it in a symmetric plane, and then we are doing CFD here. So after this, there will be some solution which are optimized, and we will use those optimized simulation to do testing of actual aircraft in wind tunnel. Then we will get to know the real time data and the problems which are occurring, and then we will optimize that real fighter aircraft there. So that is how, why CFT is used. There are some places like here in this also in the wing, jet engines is available. There also for internal flows we are using CFT. We can use CFT for airflow analysis, for combustion analysis, and some of the cars like here you can see, say it's a student go-kart or it's a F1 car kind of, and there for aerodynamic analysis we can use. In normal cars, luxury cars also we can use. But how will you simulate the you can simulate the outer aerodynamics, but for suppose somebody is sitting inside the aeroplane for, so we need to like simulate that air conditioning there also for, so for that also CFT is used. Then in this car there is a fuel tank. For that simulation, for IC engine simulation, what will you do? You will use the, suppose this is a 3D large ID simulation of that internal combustion engine here. So that also can be done. Is used in right now in industry. It's a industry standard. Some biological flows now I am sharing. Okay, let me just go through my. Okay. So first whatever I have discussed is called as aerospace application. In that interior, exterior, and combustion chamber, all of them is using. Then I shared automobile application here. In automobile industries, uh, so you can see some of the videos of Jaguar Mega Factory or Porsche. They share their aerodynamics, how they are achieving that. So first they will do CFT. After optimizing, they will go to the wind tunnel and test it like this. Okay. Third is biomedical applications, like this you can see. So this is recently we faced coronavirus challenge. So here it is a direct numerical simulation of that virus along with particles. So these are the particles of cough droplets you can say, and you can simulate it in CFT by using CFT. Uh, just not using CFT. Along with that, you have to use another uh, solver. Solver is a code. Solver is a code developed for particular thing. So it's for, like suppose for particle you are using. So you need to develop a Lagrangian solver, which is kind of simulating the particles. The particles are simulated in just by calculating the Newton second law. Okay, there are more complications which we can discuss later. This is the trachea simulation, or you can say simulation of lungs. Here also, this is a periodic. So, in this problems, what matters is boundary conditions of the CFD. So it, you can treat it like a, you don't have to design it like this. There are ways to design it like this, but also you can do it like simple. Just a second. Simple pipe. Uh, but yes, you need to apply boundary condition very carefully there in these biomedical simulations. So till this you are finding it okay, and please let me know if you are having some doubts. I'll clear it. So right now I'm just sharing a basic here because I didn't know that you guys also need to know the basics. So like basic equation solving and all, I'll do it maybe in last 1 hour. And one more suggestion I want you from you guys, that you guys need to know about the coding part, MATLAB coding. So should I do it in a MATLAB coding way? Harsh is saying yes. Okay, you want coding part. Because I'm a bit confused, like should I share the coding part or should I do just the basic equation solving and all, or for some week programming part you joined. Okay, 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 I'll try to do it. 1 hour I will dedicate to the basics, 1 hour for coding part. Maybe if some doubt is coming, because it's a live session, if somebody is asking doubt, then I have to tell him. You can also ask. Okay, no doubts till now. Are you enjoying? Okay. So other application in biomedical is simulation of red blood cells. So it's a nanoparticle, you can see red blood cells. You can also do it. So here you can see different boundary conditions are applied. So in all of the problem, you can see main thing is initial and boundary condition. These are the most important part of CFD you need to define, because if you are simulating suppose a air condition, and if you are simulating a pipe, there is no difference in that except the boundary condition and initial condition, because you are at the end you are solving the Navier-Stokes equations. So how you are solving it depends on the boundary condition and initial condition. So here you can see different boundary conditions are applied, and these are treated as particles here, red blood cells. And this is the hard simulation. Uh, so this is benefiting cardiologists a lot here right now, because they know when it is uh, like clot is happening there, how the cycles are uh, like it's varying in different human being. After some test they can measure it, so it is on the time uh, helping them. Some chemical industry example I want to give. So real time chemical industry example are suppose pharmaceutical medicines are there. So medicines can be treated if granular particles, we are treating it as granular particles. So they can be treated as continuum and behave like a fluid. So if you see the simulation of fluidized bed, their granular particle behaves like a fluid. Here also you can see when mixing happens, you can use CFT there. Okay, I need to admit. Okay, fine. So there also we can use it as a CFT, and normal chemical mixing problems. Here it is a cooling problem, and normal industries we can use CFT. So okay, let me go to another. So right now I'm using system, computers, and suppose somebody in a cloud. Uh, we are using this Google Meet, and it is operating from a cloud, Google Cloud, and data is saving there in Google Cloud. So there are data centers there in which it is saving. So for that cooling is needed, and cooling should go in each and every bit. Uh, if it is not happening, then what will happen? It will burn out, that and it will fail. So it's a big system. You can do the particular point heat transfer simulation with the help of CFD. So if suppose here 10 CPUs are sitting in this rack, and you want to know the where is the highest point of heat generation, you can simulate it with CFD. There are people simulating before installing of that. After that also you can pinpoint and increase the cooling at that point. So it's very helpful. And in my system, suppose I am using a system in which IC is there, chip is there. So which is cooling by forced convection, sometimes by a fan. In recent MacBooks and some of the other PCs, it is uh, liquid cooling. Right now there are some ROG laptops, Republic of Gamers, in which they are providing a liquid cooling setup in the laptop so that heat will not generate in the IC. If that happens, CPU will burn out, and it is like it will fail your system. Uh, there are other applications. Suppose we are simulating a dam. You can see this GIF in which you can do the simulation of when dam will fail. So it will be a fluid structure interaction problem. And here also the erosion, what kind of erosion will happen here, you can simulate that with the help of CFD. This is the video in which you can see the this failing, failing not at a very high speed but at a particular frequency, and this is currently now people are doing the simulation of this also with CFD, in which two uh, uh, turbulence structure were happening at different rotation direction. So that's why it is happening, the failure of these. And there is a concept of resonance frequency also, but people are also doing it with CFD. These are the this is the flow over a cylinder problem, in which if some um, instabilities are coming, so there are simulations with of instabilities here. So these are the best test cases for CFD engineers. You can start your simulations by doing a flow over a cylinder problem, in which Karman vortex you can see here. This is very interesting for a lot of CFD engineers. Uh, so there are marine applications also. So I just want to you to know that CFD is, you can apply CFD anywhere, even in the water, even in air, and even in granular particles like your suppose in silo flow or what in your kitchen you are pouring a bar of salt in your uh, in some jar, then you can see that it is flowing like a liquid. So there also you can apply CFD. The people are applying. So it's everywhere you can apply. It's very interesting. So suppose you want to do the sea simulation. So in marine applications, right now, most interesting area is ocean surface temperature finding, uh, or how the temperature is changing. That is current area. And another area is environmental engineering, in which you can we can do the simulation of whole earth or some part of the earth by so uh, by doing that we can forecast the weather, which you can see daily. uh, how you are seeing the weather forecasting, anybody can comment on that, uh, how weather forecasting occurs. It can be wrong, it's okay. Okay, okay, good, good. Others? So it is happening with the help of CFD, I want to say. Uh, GSRI Datta uh, software, like sir shared the MATLAB license with you, so I'll do it in MATLAB. Yeah, Arvind. Okay. Okay, but the question is, you are correct, but the question is, suppose I want to know the weather of, suppose today is 28 July. I want to predict the weather of 1st August. Then what you will do? You don't know the what will be the like what will be the temperature there. Then what will you do? You can see right now in weather.com or anywhere, you can see the temperature at that day, what will happen, it will be a rainy day or not. So how will you do it? Yeah, yeah. So it's happening with the help of CFD. So CFD, what we will do, that we will divide the whole geophysical domain in some part. So the grids, like division of the grids will be like 1 kilometer grid, 5 kilometer grid, and then we will do a simulation in our system. But it's not a normal simulation. It's a parallel simulation. Parallel means, uh, uh, suppose a supercomputer is working. Supercomputer is a cluster of computers. You can see lot of computers are working in similar uh, simultaneously. That is called supercomputer. It's not a big giant computer. For those who don't know about supercomputer, it's a, suppose 10 computers are working together, it's called supercomputer. So there we will solve those uh, like equations there, and we will predict the data. So it should be on real time. That's why we need more and more fast supercomputer to predict for future. So that is the thing for predicting the weather. So this is happening with the help of CDEC, India. And suppose in this, it is it is floating on the surface of ocean, and some turbine is there for running it. So how it is moving, how turbine blades are moving with water, how it is uh, giving the thrust uh, to the ship, you can predict. How, when it will fail also you can predict with the help of CFD. It will fail when cavitation happens. Okay, this is a submarine. You can do the simulation of submarine also with the help of CFD. There are problems of defense, like defense problem or navy problems. You can do it with CFD, and it is it is doable only with CFD right now. Suppose you want to throw a grenade and you want to do the simulation of that. It is also possible with the help of CFD. You want to do the simulation of fish, it is also possible. So everything is possible here and there with the help of, with different solvers. I must say, solvers are in energy applications. It is like a wind turbine. If you want to design, this is also happening with CFD. And what is happening outside it, um, this is the simulation of that. And there are wind farms, there are solar farms. You can predict. Suppose this is the turbo machinery design of this. You can predict by this. But suppose right now we are mostly focusing on renewable energy. Renewable energy, one major source is solar power. So solar farms, they call it solar farm. How solar farms should be designed, where to place that solar panel in a big farm. Suppose 10 kilometer or 2 kilometer farm is there, how the wind will flow through it so that we will get the optimized uh, electricity. There we need the use of CFD. And lot of wind turbines are there, there also we will need CFD. In sports dynamics also, now it's interesting for most of us. Suppose I am riding a cycle and the wind is flowing, so I want to win the race. How will I win? So I will decide at which angle should I uh, ride this cycle, and where to set, where the sheet should be there. So these are all optimized, then player will go. So how the design of cap will be, my helmet design, where to put my hands, everything is contributing towards reducing the aerodynamic drag. So if we want to reduce the aerodynamic drag, that's why we are doing CFD here. You have must have seen some memes about it. Some guy is riding behind some guy, and he is not doing anything, and because all of the drag is taken care by this guy, so behind that there will be less drag. So it is helping him, and this can also be designed for swimmers. Suppose Olympic swimmers are there in our country, we want to contribute, so we will put them in a wind tunnel, and we will see their hand motion where it is going. So it is happening right now in China for Olympic players, how they can be optimized to win the more prizes. So they are telling them where to put their hand, how to rotate their hand, everything. So you can see here, it's happening in a wind tunnel or water tunnel also you can use. So this is the simulation of a cricket, some ball. I don't know, baseball ball, I think. So here also, what is happening back in the back of the ball? There, like this is the vortices generating um, behind the this ball, spherical ball. So how it is contributing towards the drag and everything, we can design there and see how shuttlecock of a badminton shuttlecock also is designed. And F1 racing is also a part of sports. That's why I have included it, which we have covered. So here splitter is there, spoiler is there. Sorry, spoiler is there to reduce, to take it, make it attached to the ground. And another is this. He's a player. Is so if we can do the simulation here. Okay, I think yeah, natural flows like volcanic eruptions. If you want to do this high speed turbulent flow, so uh, now let me introduce you to one topic. If you guys have any question regarding the course, means in the course you face any problem except the basic part, you can tell me right now. I will try to cover it. Except I will start my thing. Whatever I will teach, I will start. I'm new to CFT, doesn't know much about CFT. I heard little about ANSYS CFT. Okay, okay. That okay. I'll cover that. Why you can use MATLAB? It's MATLAB is like you are generating another ANSYS kind of. You can see. I'll tell GSRI Datta. I'll tell. I don't know what's your name, but Datta I'll call Datta Krishna. I'll tell. I'll tell that why you are using MATLAB. And I will do some hands-on things also in MATLAB. I can do it. You will know. Just be relaxed. You will know why you are using MATLAB, not ANSYS. Because ANSYS, okay. Others will we also learn math behind meshing? Yeah, sure. Harsh, sure. I'll try to cover it. I don't know. I will do justification or not, but I will try to cover. I understand your problems, all of you guys. I know what problems you are facing. Today is the first class, that's why I'm asking lot and wasting some time so that I get to know about your problems. It's every week. Yeah. Once okay, I think okay, somebody's yeah, fine. Okay, only 13%. Let me start. Okay, so volcanic eruption is, so there are okay, I'll share my screen there. All of you can see my iPad screen. Just comment yes. Oh, sorry. Just say yes. I can't see. Open queue. Okay. Now I am sharing my iPad screen. Please let me know if you can see the screen. Otherwise, I will do it by again connecting it. I think I have to connect it. Just wait for 2-3 minutes. I'll connect it. Yes, please say. I am not getting anything. Because I am getting confused whether I am visible. My screen is visible or not. Arvind, please. Arvind. Yeah. Chinmay. Okay. Because I lost something there. So that's why I'm asking. Okay, so just now for completion, I'll tell. There are natural cold dust explosion, as I told. So this is the simulation of Beirut explosion. So just few years ago, 1 or 2 years ago, we heard about Beirut explosion. You guys know about Beirut explosion. So that yeah, Lebanon, yeah. So there it is. This is the starting point of that explosion, and these are the buildings, which some this Viper Blast SSL they have simulated. I just took it from their website, so you can see these buildings and all, and you can analyze how that happened, what are the impacts, and how far the impact has gone. You can simulate it. So it's one of the good CFD simulations of heterogeneous explosive, because we don't know what causes it to explode. This is the normal explosive like a grenade. Here also shock, turbulence. Shock is this is shock, which a shock right now I'm not defining, but this is shock, you can say. So this is the combination of shock, high speed turbulence, uh, um, high speed turbulence, and granular particles and combustion, everything. This is a combination of that, and this is called as high speed turbulence flows. So let me see. Okay, what's this? Just a second, just a second. I am facing some problem. So just a second. Basics. This is the material processing. In material science also, there are a lot of applications of CFD. Okay, so these are the things I will tell today. Mm, Let me do it by starting from this. Yeah. Actually, I'm facing some problem by for connecting my iPad. Yeah, this. The screen sharing, sorry. Just wait for some time, just because I'm doing this. This is first time happening with me. I don't know. How to do it. This is creating a problem on sharing screen again. Settings. Okay, so what I will do is I will try it, but I will keep on moving. Sorry, guys. I want to cover it, but yeah, I'm facing a problem. So can you guys wait for 5 minutes? I'll just try to do it because yeah, no, it's a time waste, but I have to do it. Then what you guys can do is you can write your questions, specific questions in the chat box, so that later I will write it and proper questions, so that next week I will cover it. This week also I will cover, but right now I'm facing some problem. So let me do it. You start writing it, so that time will not be wasted. Here also, like right now I'm first doing it. Safari settings for this website. Can you, are you starting? Like, somebody can write at least. Okay, sure. As far as okay, Chinmay, I am reading your question. Mistakes, so I want to add into it. People are asking for answers, you are saying, other built-in solver. Since in this code we will be building our solver and we will also get exposure, say answers. This is for basics. Actually, you know answers. Okay, suppose you know the flow of answers, how that is working. One fluent, suppose you know. Now you need to use ice pack. Suppose one other solver in answers is ice pack, or suppose you want to solve it for CFX. Suppose turbo machinery you want to use it. How will you do it if you don't know the basics how ANSYS is built? Suppose they suddenly say to you that you use new solver. If you don't know the basics, how will you define the boundary conditions there? In ANSYS, Siemens, whatever you are like, their solvers are available. How will you define the boundary conditions if they are not giving it to you? So it's the flow. If you know, it's for just BTech students starting their thing. But if for the real time problems, uh, if you need to do it, uh, I don't know how you will do without basics. You need to know basics. So MATLAB, the difference is nothing actually. How it's how ANSYS is built. Let's discuss that. They are There are some codes written behind that screen. It's a suppose um, something is there. There is code running behind that. So it's same as ANSYS. ANSYS is a framework UI. Behind that, some equations are running. You will select. Suppose you select. I want to do a pipe flow simulation in which the boundary conditions are, this is will be a slip conditions. In this, boundary layer will form viscous flow. Some solver you selected, suppose simple algorithm you selected for solving it. Another thing also you selected, suppose some fluid you selected as water. So there it is, water is written behind that screen. In solver, when you solve, it is there. So while solving in MATLAB, what you will do, you will define that everything. Suppose you are defining water you will define uh, what are the properties of that water. So in your MATLAB code, you will, it's a MATLAB code. MATLAB is a coding language basically. It's not like ANSYS and all. It's a coding language. There you can um, code like yeah, code like suppose a calculator is there. I want to just be similar. This is a calculator. It is also programmed. So you think it as an answers. So here I will type 2 plus 3. It will become 5. Okay. But suppose for coding it, what it has done, you don't know. Behind that something, some coding is there. How it is solving. So for that you are using MATLAB to get to know what is the basics of that. So there it will convert that into the suppose 1 1 1, and then it will solve by adding it, how addition is working. So you need to define those things. Not that basic, but yeah, you need to define basics. Suppose how discretization is done, how you are applying. In the first three lecture you must have learned about upwinding schemes, how that upwinding schemes are contributing, and sorry, are there. You are applying center difference, so you can see when you are applying a center difference scheme or upwinding scheme, or different, like forward difference, uh, what is the difference coming while you are applying that in MATLAB, you can see. So it's just a coding language what you will apply to see different mathematical problems. It's a basically a matrix solver. So whenever you will define a CFD equations, uh, d- a finite difference CFD equation, or uh, a differential equation you will define in a different way. There, for solving that, you need to, like, you will define it in a matrix form. After defining in a matrix form, you will do calculation, like how that A cross B, A matrix dot B matrix. You, all of you know from linear algebra, that A matrix dot B matrix, how that is multiplied, or how you can calculate that A inverse. So that's, here we are solving that A inverse in CFT. For showing how it is happening, we can solve it in MATLAB. MATLAB is, full form of MATLAB is Matrix Laboratory. Means you can solve different matrices there basically. One more thing, you can do it in basic language like C. C also, it is also equally applicable. But the problem with C, it is not built in there to solve matrix. So how that is multiplying that matrix, also you have to define there. So uh, yeah, now I think you got something why we are using MATLAB. Sorry if I confused you. uh, Chinmay? Yeah, now you got why why we are using MATLAB. Exactly. And there also you can build your solver in MATLAB. Like suppose you want to build it for re-entry flows. Re-entry flows for everyone. It's when something is going into the, like Chandrayaan is going from orbit to the uh, surface of moon. That is re-entry. So there you need to use different solvers. Suppose something is not available in ANSYS, how will you build it? It's a building thing. So there we need to use that. I'm still facing problem in my iPad. I don't know, this is first time I'm facing. So, uh, hmm. MATLAB. mm, I think it should work in offline mode also. It's working, okay. Yeah, you install app, and it's, there is one student license also available, you can use it. Okay. Yeah, this will be working till course is there, so you can use it for student purposes right now. Yeah, yeah. Didn't got your point. Okay, that you are asking. There are ways in which you can couple it. So, and suppose you are using ANSYS. Okay, so for ANSYS, just a second. I want to connect it this today at least. I think I connected. I will happy about it. Visible? Thank God. Yeah, that's nice. Yeah, okay. Now I'll be more comfortable. Okay, so what you asked is connecting that thing. So this is ANSYS. Suppose this is ANSYS screen. Okay, so you have one option called UDF. Uh, some functions you can define. So if you have written a code in MATLAB, like you have written a code for solving a suppose 2D heat transfer equation, which is not available in ANSYS. It's a just uh, assumption. It's available, but right now I'm assuming it's not available for 2D. Or suppose an in Navier-Stokes equation, you have a term of magnetohydrodynamics. Some magnet is there and a fluid is attracted towards that. So you have magnetohydrodynamics. Okay, you want to apply in you have applied in MATLAB already. Now you want to do it in ANSYS. What you will do, you will just copy that code in ANSYS uh, UDFs. There are UDFs, you can copy that and then you can use it. One more thing, you can couple it with MATLAB. So there are coupling softwares, by that you can couple. Um, but mostly people generate their own solver if they want in MATLAB directly. They will not couple it. Uh, yeah, there are things available for coupling, but it's for if you have written a very big code, then only you need to couple it. Like suppose I have written a code for solving something in MATLAB, proper code, 10,000 lines code I have written in MATLAB, and now I have to couple it with Navier-Stokes equation also. So I can couple it with ANSYS. There are ways, but right now I think you don't need it. You don't need it, right? Mm, that I'm not very sure about it, but uh, yeah, that is what I said. That whatever language it is. So you are concerned about language right now. It's language is nothing actually when you are dealing with these simulations. If you have done it in your logic, you have applied it in MATLAB, you can directly do it in C also. Uh, I know it. Coupling is different thing. If I am coupling, if I am using some coupling software, then you don't need to change your code. That's for sure. It will be there in MATLAB, running in MATLAB itself, and another part is running in ANSYS. You need to just couple it. So it will supply this output to this coupling software. So one coupling software is, I think, Precise. If you need later, I'm just telling. It's a very high level thing, or I can say it's a very after you have done lot of things, then you can use it. But yeah, this is a code, or you can say ANSYS kind of software, where what will happen? You have I have ANSYS, I have COMSOL, I have MATLAB, and I have C. Four codes I have, suppose. So what it will do, it will take the output from ANSYS, and if path you need to define, then it will supply it to C language code, take the output of C language code, supply it to MATLAB, and take the output of MATLAB code and ANSYS code, supply it to them. So you can play in this software. It's a coupling software basically. Am I clear? Yeah, so for that you need to define, like first you need to do the drawing in any of the software. Then you need to take out the STL files. STL files are the files which have the coordinates of that. So every coordinate, so it will be taken in that MATLAB, and in a code you need to define. There are ways. I'll tell in during the coursework. I'll tell this also. That's the part of the course. Yeah. For sure, if you follow it, because there are assignments also after 1 or 2 weeks. There are coding assignments. For that also only I am covering. For that, sir has given you that MATLAB license. So you need to do it in like you need to write your own code. That's not very difficult. That I must say. I know you will be feeling that I am saying not difficult because I know, but I know that it is not that difficult. Um I can teach you some MATLAB things also in starting if you want. Just let me know like how to do it in MATLAB, how to write a code in MATLAB. That also I will cover in this. So I think I have to cover a lot in this. Fine. Okay. So should I start? Uh, yeah, I think I will start. Okay. This. Uh, just a second. Change layout. Yeah, fine. Let me start with fundamental principle of conservation. So it's total fluid mechanics and everything is based on the fundamental principle of conservation. Let me start giving an example of bank in which you put, suppose you are going to a bank. It's given by one of my professor. I am just copying him. Okay. So suppose this is a bank. You are going there with a money, with some money. So you are putting in something, some money you are putting it, and now you need it after some more months. So you are taking it out. Will there be something left there? Anyone can tell. It's easy thing. Yeah, but suppose like I have put in 10,000 rupees for 4 months, interest will be there. Okay, yeah. So I can call it as a generation. Will this be fine? Yeah. Okay. So just remove this bank. Okay. Uh, this is actually the like suppose. So let's do it mathematically. What is input? Oh, sorry, some other pen I can use. Blue. Okay, so we can do input. Some money in is there. Okay, I am taking out some money plus interest generation. Okay, these three things are there, and this will be my total change. Fine. Is it okay? Okay, just apply. This is, you will be surprised that this is the principle of conservation in fluid mechanics also. You will put something there will be, suppose I am putting a heat source here and I am taking out some heat from here, there will be some heat generation here, and it will be conserved. So you know the first law of thermodynamics, everything, energy need to be conserved. Same with, you will put some water here, something will coming out. If some, it will be some loss also, some loss can also happen. So its generation, it's algebraic quantity, it can be positive, negative. So you just put here rate of, and rate of. So this is the rate of coming in. Rate means per second, per hour, how much flow is coming. So that is called rate. So actually the uh, now I think the conservation principle is clear for everyone. Okay, you can just say yes if it is clear. Not clear, then again I will explain. Yes, it's clear. Okay, okay. So the problem after this, what we will face is all the conservation, like basic Navier-Stokes equations on, suppose basic Newton's equation of motion, and thermodynamics. Just wait, I will write. For you I am writing actually. Thermodynamics equation are not developed for Eulerian description. So I will now description. Eulerian description and Lagrangian description. There are two description. I will also do it faster. So suppose I have lot of particles here, and I can treat it in a way in which I don't have to be concerned with one particle. Suppose air in my room, I am sitting. I can't see a single particle of air. So air here is enough to take it as a continuum. Means if I treat it, all the particles as same, I can treat it in a way in which all the particles will behave in a similar fashion. But suppose I have a box here like this. I have a box in which I have created a vacuum, and I have some particles left. So I can't say they will behave same. They will go in a random manner. So their kinetic theory will work. Okay. Okay. Yeah. Their kinetic theory will work, and only you must have read about kinetic theory, Brownian motion, everything. So here I can apply Newton's second law for each particle. It will work for sure. It will work. So I think it's clear. So it is called Lagrangian, in which every particles we have to take care. Lagrangian. So everything. Suppose this block, we are applying a Newton's second law there. So it is in the Lagrangian fashion because it's one block for solid mechanics. For fluid mechanics also, if we need to apply this Newton's second law, it's described mostly in a Lagrangian way. But how will you do it in a Eulerian fashion? For that, there is no or nothing. But let me write it. Okay. Different for Lagrangian description. I think it is clear that Newton's second law is for Lagrangian description, but right now I have to apply it to Eulerian description. For that, I have to use Reynolds transport theorem. So what it will do, it will convert those equations in Lagrangian manner to Eulerian manner, so that we can use it in our fluid simulations. Transport theorem. So, I am just giving an example. Suppose this is a system, which we read it mostly in thermodynamics, and the system moves from here to here, and I am doing it in a very zoomed way. So it's a at time t and time t plus delta t, so it's an infinite decimal distance it covered. I am doing it in a zoomed way, so it will behave like it has covered lot, but it's a very small distance it covered. So system at one point, and say another point it is there. So okay, this okay. Today I don't know why. Yeah. Okay. So suppose some properties are there with this system, which I am calling at n, and I am defining it as extensive property. uh, I am presuming that you know about extensive and intensive property, so not defining everything here. And at t is, so one more thing, this is 1, this is second, and this is third. So what is common? Second is common in all of them. So n at t, the properties total is a combination of n1 of at t plus n second and second whatever the properties are there at t. And so n is a property in of the system, any property, and n at t plus delta t is there. So n second, in second whatever is available at t plus delta t, plus n second and third at t plus delta t. Am I clear? At t plus delta t and t there are properties. What's the change we need to define? So what we will do for defining the change, we will do dn by dt of system. This is how we are making it in a partial differential equation form. So what we will apply, because it's a okay, let me do it simply. N at t plus delta t, this minus this is this, simple. N at t plus delta t minus n at t divided by delta t, because this is delta t. But this delta t should be limiting to 0, because we have just moved infinitesimal distance, so delta t should be 0. So what I will do, dn by dt of system is equal to limiting of delta t tends to 0, and like you can stop me at any point if you don't get it. So I am just opening this. Okay, let me write it in a bit shorter form. Yeah, dn by dt system is equal to limiting delta t tends to 0. And what is this? Let's just open it. And second, so let me not try it. Okay, so let me write it. Plus n third of t plus delta t minus nt, and t is n1 t plus n second t divided by delta t. It is clear to everyone, I think. Now limiting delta t tends to 0, same. Now I will just take n second what is happening, second t plus delta t minus n second t by delta t, it's there. And another r, what is left is plus n third t plus delta t, it's third, minus n1 t by delta t. It's clear? Now I will move to the main point, which is limit. I have to reduce the size. Yeah. Limit delta t tends to 0. This will remain same. Okay, I'll just do n second t plus delta t minus n second t by delta t. And what is this? You just see. And what is leaving from here? Sorry. What is leaving from here and what is coming from here? So this is the rate of change, which, so n third t plus delta t is rate of outflow of property. Whatever is going from here, it's rate of outflow we are defining, minus whatever is coming is rate of inflow. I will not write inflow. Fine. Of the property across the domain, across the system. Am I clear? Okay. Then what will happen if just this delta t tends to 0 and system is tending towards a control volume? What will happen? What will happen? I'll tell you. If suppose in second is the second part is tending to the control volume, it's a control volume whatever we have defined, and when delta t is tending towards 0, which we have defined, and system is tending towards this control volume. So system is tending towards the control volume, then what will happen? This will we can define it's a partial derivative of dn by dt of that control volume. So why partial derivative? Because we are fixing the position and varying it in a time. So position is fixed, one thing is fixed, position is fixed, that it is there at second, that is fixed. That's why we are defining it a partial derivative, because one thing we are taking it as a dependent variable. That's why n plus what will be there? Suppose it's generally I have defined a surface where a property is leaving at velocity v. It's a vector v. So we have to define a normal vector here, which is n cap. Okay, and the area of this is dA. Fine. And here we have defined n as extensive property. So per unit mass, what will be this? Small n by mass, which is a intensive property. Just bear with me for some time, you will understand why I am doing it, everything. So in control volume, what will happen for inflow and outflow? This n into mass, which is rho into v into n, small n, sorry, there will be a difference in this, small n into rho v into delta a at a particular direction, which is n cap, is a normal direction. So total transport property will be this, total transport. If there is some problem in math, just tell me right now. I'll clear it, because it's very important here. So I am dealing with total derivative of system, whatever the properties are going from the system and coming, and what is the change is dn by dt into the control volume plus rho small n is the intensive property. V relative means from the control volume, what's the relative between that and in the normal direction into dA. It's in the control surface. In this is Reynolds transport theorem. So why we have done this derivation, I will explain. From this from this equation theorem, we can we can derive mass conservation, we can derive energy conservation, we can derive momentum conservation, and that momentum conservation is Navier-Stokes equation. So Navier-Stokes equation is nothing, it's just Newton's second law applied to a fluid particle. Simple. I hope everyone is getting it in the mathematical sense also. Okay, someone wants to join the call. Sukhdev. Yeah. Anybody facing problem in mathematics? You can ask me next week also. It's fine. I understand it's a bit difficult thing, but till this I think it's not difficult. And whatever is leaving from here and coming from a control surface, because it something is leaving, it should leave from the surface only. It's not volume phenomena. That's why here we are using control surface, and it's a like rate of change is happening inside the volume. That's why we are doing it in a control volume sense. VR is relative velocity of system and control volume. Okay, Krishna, you can ask. No, you can ask. You can ask. Yeah. Actually, here the total property is how will you calculate? N is N by M. M is rho into V. Okay. So what I am doing is N is equal to rho into V. Yeah. Yeah. Actually, right now, whatever we are doing is for extensive property only. So let me start it from here. I have done it for extensive property totally from starting. Okay, you just see this. And now, for rate, I can't define it in an extensive property manner. For rate, because yeah, understood. You can ask me next week also. It's fine if it is not clear. I'll explain it in a more extensive way. If it is not clear, you just revise it, and if it is not clear, because main thing is this, you just uh, consider this as the main thing so that we can. Hmm, yeah, yeah, yeah. Oh, okay. Suddenly it converted to inside because it's a area phenomena. That's why we have to do it. Nothing else. Yeah, inside. Yeah, Krishna. Yeah, control surface. Okay. Here, if something is going out from this surface, so I have defined it like this. So this is the control surface we are using in that. Yeah. I didn't understand your question. Can you again say? This one? Yeah. Mm-hmm. but when I have done this, then I have taken these assumptions. You can see second is a control volume, second part, and the system is converting into the system, like, because it's, I have said I am just telling this in a zoomed way. Later I will convert that to a single frame, because it's an infinitesimal distance it covered, so it will come to that second only. There are very less part which is covered, so those 1 and 2 are covered here in this part, in this rate of change, and this is the control volume. So those rate of change will go, I think I'm not very clear in this. So this is very less change here, very less change, infinitesimal. And now I am considering this second, because this is the rate of inflow, this is the rate of outflow, but this total is a control volume total. Like this total means, uh, we have not moved very far, so that we can convert to that total as a control volume, and these as a control surfaces. That's it. So it's a one system only. It just moved a bit. We consider that delta t tends to 0, then consider it as a control volume. Am I clear? Yeah, I will try to be more clear next week. Maybe if somebody again asks question, I will try to be more clear. Right now, what is happening is I am just telling you by my memory, because I never expected that basics I have to teach right now. It's fine. Uh, I'll be more like, I'll also revise something in this. So today, I think, yeah, I have some 20 minutes. I will solve mass conservation, so that I think will be very clear for all of you why we have done this derivation of Reynolds transport theorem. And one more announcement is that next week for 1 hour I will directly cover basic, 1 hour for MATLAB. I will MATLAB coding. I will cover in that. So I'll prepare some more slides and all. So n, uh, suppose I am doing it for mass conservation equation right now. So n is an extensive property. Okay, and our equation is this. This our n is now mass. Okay, mass is also extensive property, but for intensive, what will be this? N by m by m, which will be 1. Am I clear? So let's take for example 1, which is conservation of mass. Let's apply this equation for conservation of mass. Okay, how will you apply? You just do it. Dm by dt, and I am putting it as m. Okay, system d is m by dt, control volume. And as all of you know, for system, mass is conserved, so it should be 0. And here rho, and for small n I am putting 1. Am I okay? And then the relative velocity, and then n, then dA. It should be clear from here. Okay, so mass of system actually doesn't change with time. Whole system's mass doesn't change because it is conserved as we are dealing it with. So we have done it 0. It should be clear. Like mass of, like I have a fluid particle, its mass should be conserved. Its mass should be 0. Change in mass with time, it should be 0. That's whole system. But in control volume, it can change. So what should I do is, because yeah, let me be more clear. System, for system, system is something with a fixed mass. That's definition of system. Let me write. Definition of system. System is something with a fixed mass. So you have defined something as system with fixed mass. Then only you can say it is a system. I think everybody agree. Okay. 0 is equal to uh, del over del t. And one thing I am assuming here, it's a non-deformable control volume. Non-deformable means, uh, what I can do is, I can write this m as integral of rho dv, and v is volume here. That cut v is volume I am defining, because I don't want to confuse you with velocity. So this cut v is actually volume. So rho dv is mass integral. So how will you write? It's rho dv of control volume. Can I write? Like, you can comment anytime. If am I not confusing you? At least that shows. It's bit mathematically intensive, I know, but yeah, for someone it can be a bit difficult. So I can explain it more. But it's very simple. I have just apply here. I have, sorry. I have put I put n as capital N as small m, and small n as 1, because it's an intensive property. Here, dm by dt of system, total change in mass of the system should be 0. That's why I have put it as 0, because system is always with a fixed mass. 0 I have put it. Then m is integral of rho dv, that rho into v everyone know, m is rho into v. So integral of dm is rho dv. That's okay. This is there, this is there. I have changed nothing here. So now two assumptions we need to take. One is, to put it inside this integral, we need to have a non-deformable control volume. Why? So first assumption is non-deformable control volume. Why I am taking this, I'll clear. Because volume of the control volume should not be a function of time. Right now we have assumed volume of the control volume is not a function of time. Means volume of control volume is not changing with time, or like is not influenced by the time. It's the assumption we have taken, so that we can put this partial differential inside this integral. Directly we can't put it. And another is, for that system, we have assumed is having some relative velocity with the control volume. But right now we have to assume second assumption is control volume is stationary. Means VR should be equal to V of the control volume. V is the stationary control volume. Okay. So 0 equal to, in this equation I am putting everything. So I can put, because of the assumption of non-deformable control volume, I can put d by dt of rho dv here, plus rho 1 v into n cap into dA. Till this, am I clear? This is in control volume, this is in control surface. Yeah. Then again, I need to apply a mathematical uh, theorem. You can say it's Green's theorem. Everybody have read it. So how will you convert area into volume? So control surface into control volume, I will calculate is suppose some A B dot eta is there, dot dA is there. Uh, C, suppose C is there because I am writing area also. So I have to control this control surface and control volume. What I will do is convert by rho CB into dV. Rho dot. So it's a mathematical theorem. You can directly see it. It's like you don't have to know everything about mathematical theorem. You can directly see that this will convert into rho dot dV into dV. So by Green's theorem, it converted. So I have this right now, control volume of del over del T of rho dV plus del control volume of dot rho V dV is equal to 0. So right now what I can do is I can have this integral, both are same. I can have a control volume integral here, del rho over del T plus rho dot, sorry, del dot rho V into dV is equal to 0. Right now I will take a arbitrary control volume and make it integrand as 0. If I take arbitrary, so let me write also, should be control volume choice is arbitrary, then only I can write del rho by del T plus del dot rho V equal to 0, this integrand, and this is nothing but conservation of mass equation. So I will do it for incompressible, where del rho by del T is 0 plus del dot rho V is equal to 0, which is, if I take del out because it's a constant there in incompressible, so I will write incompressible, means density is not changing. There del rho by del T is 0 and this rho can be out, so which is, so one solution will be del by del x of u plus del by del y of v is 0. This I think everybody is familiar with. And oh sorry, this is called as conservation of continuity equation. So this is how that continuity equation is derived. I think I have not confused you, but it's a bit mathematically intensive. But yeah, you should know how it is derived. You don't need to like wrote it, or you don't need to do it in your memory and everything. You just need to know how it is derived. So this is the equation which we will use, or this is the basic for deriving this continuity equation. Now later in another class I will tell you about Navier-Stokes equation, how that is discretized, and another class will not be that mathematically intensive, I must say. I did it deliberately so that you will know how it is derived and how everything is happening there. So basics should be clear. If these basics are clear, uh, I can directly write Navier-Stokes equation. There you need to use a form for solving your fluid flow problem. Simple. So this is the way. If you define it as a, like there you have defined M as intensive property. If you define suppose MV as your intensive property, then it's a derivation of conservation of momentum. And if you define temperature, then it's a derivation of conservation of energy. These three equations make the basis for CFD: conservation of mass, continuity equation; conservation of momentum, which is Navier-Stokes equation; conservation of energy. These three equation makes the basics of CFD, which you need to discretize. So after in just 5 minutes, I will tell one thing. What is CFD? And suppose this is the domain I need to solve. I have a point from where uh, I am. Suppose this is okay. Let me be more clear. This is something cooking on gas stove. This I think everybody will. I can say that they know. Something is cooking. Some milk is boiling. Suppose. So from here we are supplying the. Suppose a point source is there which is supplying heat from here. So it will go everywhere. How will you solve this? You just need to do it in a. You just need to divide. It's called divide and conquer. Okay. You just need to, if you are doing it for simulation. In experiments you can see the temperatures and all, but here you need to divide it. Then for after dividing, what you will do, for each node you will know the temperature. Suppose temperature you know here. How will you know? You solve Navier-Stokes equation here or energy equation here. At each for each division you need to solve energy equation or Navier-Stokes equation. Then you will know the temperature here. And now I know that suppose somebody will say I want to know the temperature in this part of milk. What I will do, I will see these temperatures and make this diagram. Suppose temperature plot I need to put. So what I will do, I will do this thing, because the temperature of like this, it is highest at the end and lowest at the free surface. It is just an example of milk boiling. It's a very crude example I have given. Yeah, somebody need to ask some question. Want to ask? Yeah, we can discuss. Yeah, contour plots. Actually, suppose you divide it and you know the temperature now after solving energy equation. So you know the basics of am I clear with the basics of discretization? Why I have discretized? So you now suppose this I am taking in a zoomed view. This is the wall or milk. There you know the temperature at each point. So don't take milk as a very good example. It's a very bad example. But I am just for to know you, to make you familiarize. So this part of the milk I have taken, and I know the T0 here, T1, T2, T3 and T4 here. So according to you, what should be the maximum? It should be, I think, T0, because it's near to the burner. So if I want to plot it, how will I plot? T0, if I am plotting, it should be highest, and according to the location I am plotting, and it should go like this. It's an example, nothing more. I am not solving anything right now. When I solve, I'll let you know what I am solving exactly. But it was just an example, basic example in which you can solve different things. Why CFD? How you will do CFD? Discretize, solve Navier-Stokes equation at each point, get properties whatever you require. Then that is why you are doing CFD. Am I clear? You guys need to participate. Yeah. Because if you want to know the basics, it's, yeah. I'll share this notes. It's not very good condition, in very good condition, but I'll share by clearing something up. Okay. Okay. I think. Yeah, yeah. You will get recording. Yeah, you will get recording. I think it's recording. Yeah, it's recording. Yeah. Okay, guys. Let's meet next week. My email ID I'm writing here. Okay. Uh, just don't like, if you specifically need something, then only message me. You can ask your questions also. Please write it. Then I will end the meeting. Thank you. You guys are actually really nice participating in this. Uh, if you guys want, I can share last year's weekly sessions videos. There I have covered a lot of basics as compared to this. I'll share. Next week I will share. Okay. Fine. Fine. Yeah. Okay. Bye. Good night. Yeah.